Hello and welcome to Landscape Irrigation Week 2. This week we're going to be talking about obtaining site information and determining irrigation requirements through evapotranspiration. We'll be talking about information from the Rainbird Landscape Irrigation Design Manual, Chapters 2 and 3, along with information from the CIMIS website and also the CIMIS publications. In these chapters, what we'll be learning about is what information you need to gather at a potential job site, the irrigation requirements from an evapotranspiration reference perspective, how water behaves in various types of soils, available water, maximum precipitation rates by soil type and slope, and know the various climate zones in California, and determine peak evapotranspiration for your region. Okay, this page is from the Rainbird textbook, page 16, and it may look familiar because this is the same drawing that you'll see throughout the textbook, and as each chapter progresses, there'll be changes made to these plan pages. So this particular page is where they've made some notes of anything noteworthy that they have discovered at the job site in place, and also where they may be wanting to put some things later on the plan. So in these particular notes, they're indicating the wind direction, the type of soil, where trees and shrubs are located, where gravel and mulch will be used. Any elevation changes are also noted on this page. Normally you would indicate where your north arrow is on this page. I don't see one on here, but you'd want to put one on there so that you could understand perhaps like what type of plants you would be putting where and what type of exposure they would have. So having north on the plan is important. And it's kind of an industry standard to have north at the top of the page so that if somebody hands you a set of plans, it feels natural to do it that way. Sometimes it doesn't fit on the plan real great that way, so it's good to always have a north arrow. Okay, on this slide, I'm using the same image, but I've taken information from the Rainbird page 13, which is a list of things that you should pay attention to while you're on the job site. And I've also supplemented with a few things of my own. So here we have wind direction and velocity, if you know it. Put a north arrow on your plan, where the trees are going to be located or where existing trees are located, walkways and driveways, all the buildings that are on the property, the location and type of water and the water source, the area measurements, walls and fences, slopes, and hydraulic data. So some of these have not been defined for you yet, so I'll just go over these really quick. So basically, wind direction and velocity. If you have an anemometer, which is a wind meter, you could hold it up and it will indicate which direction the wind is blowing, and it may not always blow that direction, but while you were there, you can take a note of it, and then next time you're there, you can see if it's the same. And like I mentioned on the previous slide, it's always good to have the north arrow so you know which way is up and which way isn't. Tree locations is important for a couple of reasons. One is, first of all, are they proposed trees? Are they trees that you would like to put on the property? And that would be handy for you to know and also to share with the homeowner. The other thing is, if these are existing trees, what that will do for you later is sometimes when you are planning out which way to trench something or where the pipes are going to go in the ground, you want to know where the trees are existing already, because sometimes digging in that area is not real favorable, so you might have to reroute things. So sometimes it's easier just to have that in mind before you even get started on the job. Walkways and driveways, it's important to indicate where those are going to be. Here we have a driveway. It looks like we have a walkway here. We also have some walkways in the backyard. So and once you have it on paper, then you can kind of stand back and take a look at it. But it's good to keep in mind where these walkways are going to be, because it means that you either need to go around them or you need to go under them sometimes. So it's not impossible to get underneath a walkway, but it's nice to know when you're going to need to do it and when you can avoid having to do it. Knowing where all the buildings are will help also keep track of possibly where any shaded areas might be, It could also indicate where you might put an irrigation controller if it has power, just locating anything on the map that seems significant. The location and the type of water and where it's located at, because that's going to have some sort of impact on eventually where your point of connection is going to be, and where you might put your valves. The other thing is the type of water source. Is this water source from a well, or is this municipal water, or is it even rain catchment, things like that that have become more popular in recent years. You need to know where that water is coming from. The area measurements, you'll read in this chapter, it'll talk a little bit about scale. It's important to have on your plan some sort of indication of what the scale is, and that is, on paper, how many inches equals how many feet. So you need to know what you have to work with, so that when you pull out a scale or tape measure or ruler, that you'll know that if it's 1 inch equals 10 feet, you'll be able to make some informed decisions on how to do materials takeoffs and also estimate labor, things like that. And if you don't have those measurements on there, that can mess you up if you're not really sure what you're looking at. Knowing where walls and fences are, also that could be helpful, especially if you have trenching, or if you're going to be installing a spray system. You want to make sure that you're not going to be spraying any fences. Slopes are important for a number of reasons, because of course water is going to go downhill. And the other thing is, if you'll want to know how to apply the water. So if you're applying it really fast, it's going to be running off. So you need to know if there's going to be a slope. So you may want to apply it with a low precipitation rate method, or use what they call cycle and soak, which we'll talk a little bit more about later. And that's where you have a system come on more than once in a day, so that it will irrigate for a little bit, then turn off, give it some time to soak in, come back on, and run again for a little bit longer. And then the hydraulic data is just if you were able to take some pressure measurements while you're there, you would go ahead and indicate those on the plan. Now I'm going to make one note here, is if you have more than one location on your plan where you plan on getting your water from, then you want to check it in every spot, because it's not uncommon for there to be a pressure regulating valve somewhere on the property going into the house. But it's also not uncommon for parts of the property to not be regulated. So you want to make sure that you're measuring every possible place where you would be tying in to get water. Okay, so in Chapter 3, Determining Irrigation Requirements, they talk about ET and ETO. So what is ET and what is ETO? ET is an abbreviation for evapotranspiration. And as noted here, the plant water requirement includes the water lost by evaporation into the atmosphere from the soil and the soil surface, and by transpiration, which is the amount of water used by the plant. The combination of these is evapotranspiration. We need to know what both numbers are, not just what the plant is going to be using through transpiration, but what's also evaporating at the same time, because we need to make sure that we're applying enough to cover both. So ETO stands for reference evapotranspiration, which is the maximum average rate of water used for a plant in a given climate. So reference evapotranspiration is multiplied by a crop coefficient to obtain the ET rate for a specific plant or turf. So basically they have a reference plant, and then later when you've decided on your plants, there is a multiplier given to each different type of plant, and we'll be using that in some math equations later in the semester to decide if the plant that you have needs the same amount of water as the reference plant does, or if it needs less. So we'll get to that a little bit more later. So before you start to design a system, you want to make sure that you're going to be able to supply enough water to take care of the landscape at its worst case scenario. So the worst case scenario happens to be what they call the peak evapotranspiration, or PET. So you want to make sure that in this case, in this chart that I've taken from Rainbird page 19, in a warm, dry climate like we live in, it's 0.20 to 0.25 inches per day is transpired and evaporated from the plants. So we want to make sure that we're going to be able to supplement irrigation and be able to deliver that back to the plants. Not necessarily on a daily basis, but that depends on soil, water holding capacity, root depth, things like that. But in this case, if you irrigated every other day, in the worst case scenario, you would need to apply a ½ inch because that's 0.25 times 2. So keep that in mind before you start designing a system to make sure that you're going to have enough water to be able to supply this. So you may need some help figuring out what is your peak ET. And in California, we have what's called CIMIS, California Irrigation Management Information System, where they keep track of this information for you so that you can have it readily at your fingertips and be able to find it when you need it. One of the resources that CIMIS has are these maps, and this particular map is color-coded so that you can tell the difference of where you're located and what type of zone you're in. So you may have the same color all the way across in this coastal region, so just because you're at Southern California doesn't mean that you have an exclusive zone that can't be duplicated somewhere else. So because they're color-coded, it helps you keep track. And what that means is within this zone, say here zone 1, your plants are going to have a similar evapotranspiration reference. So here in zone 4, you can see that it kind of scoots down the coast here also. So if you were designing a system for zone 4, whether it's at the top of California's coastal inland range or it's at the bottom, you can use that same reference chart for your information. If you're not quite sure exactly which zone you're in, you might have to zoom in on the map and take a look at where the little T is. Right here next to my cursor, you'll see that Santa Rosa, there's a little T right there, and it's in zone 5. And that'll help you find what you're looking for. So the next slide is going to help describe the geographic ranges. So here we have a description of what these type of ranges are like. I just pointed out Santa Rosa a minute ago. So here, number 5, northern inland valleys, valleys north of San Francisco. And then the other ones, number 1 was coastal plains, heavy fog belt, the lowest ETO in California characterized by dense fog. So because it's so coastal, there's so much fog, your evapotranspiration rates are going to be much lower, which means you'll need less supplemental watering. In contrast, here you have zone 18, Imperial Valley, Death Valley, and Palo Verde, low desert areas with high sunlight and considerable heat advection. So here you're going to have very high ETO rates. And here we have the monthly average reference ET zone chart. So it may look a little intimidating at first, but once you know what you're looking for, it's pretty easy. So if we think back to the map that we had on the last page, we had color codes for each zone. That color code has transferred over to this chart. So zone 1 was a very cool violet color, and as you transfer down, it starts to lose its color, and by the time it gets to 18, it's kind of this rusty color here. Being that we were talking about zone 5 on that last map for Santa Rosa, let's look at zone 5. So once you have figured out which zone you're working in, then the rest doesn't matter quite as much as far as, looking at this in its entirety. So here you have zone 5, and then across this axis you have all of the months of the year, and then a total, and that's the total ETO for the entire year. So if we're looking for peak ET, what we'd be looking for is the highest number in this row. In this particular case, January has a pretty low ETO because we have a lot of rainfall and it's cooler months at that time. And then you'll start seeing the numbers get a little bit higher and higher until finally you've reached July, and in zone 5, that is your highest ETO month. So that would be our peak month, would be 6.51 inches for July. And then you'll see that it starts going back down for the rest of the year. And then in zone 5, the annual ETO is 43.9. In contrast to that, what you'll see as in these drier areas, like in zone 17 or 18, the peak month is also July, but look how much higher this is. Zone 17 is 9.92 inches, and 5 is 6.51 inches, so quite a bit more. And then if you look at the annual total, Santa Rosa was 43.9, and zone 17 was 66.5, so quite a bit more. Okay, so the chart on the previous page was historical averages. This page, what it's going to give you is what actually happened recently. And you can break it down by daily or monthly or annually. And what I chose to do was get a monthly average for a year. And I picked station 106, which is in the Sunel Valley, which is up near the Ukiah area. And what I have here is the dates from August 2019 to July 2020. And this also can seem a little bit intimidating at first, so you want to just kind of keep track of what it is that you're trying to find out. And in this case, what I'd like to know is what was the total ETO? So here we have August through December had an ETO of 19.24 inches. And then from January to July this year, it was 33.55. So I could add those together to get my total. One other thing that you may want to pay attention to here is how much total precipitation. So total precipitation is going to be how much did it rain during that period of time. And in this particular case, this is summertime. You're going to see very little right here. Until November, it only rained about 2 inches, and then in December it raised up a little bit more, and for the total between August and December was 7.9 inches of rain. And then as you came into 2020, there was a little bit of rain in January, very little in February, some more in March, a little in April, some more in May, for a total of 7.2. So some cities, when you're trying to calculate what your water budget is going to be, some of them have you subtract out what your total precipitation is. So in that case, you would add up all of your ETO and then subtract all of your total precipitation. But more likely, what it will do is they'll say, okay, some of that rainfall that you received was not beneficial, and it depends on how much it was. So sometimes what they'll do is they'll say, let's take 25% of the value of all of the rainfall that you received, and we're going to subtract that out of your budget and subtract it out of your ETO, and that's how much your water budget will be your ETO minus 25% of your rainfall will be how much your water budget is going to be. Okay, so now I went ahead and took that chart, narrowed it down to just one zone, and I'm using zone 8 as an example now. So zone 8's peak ET, or highest ETO month, is July at 7.44 inches. So now I'm going to show you how to break that down to your daily ETO. So what you do is you take this 7.44 inches and you divide it by the number of days that are in that month. Well, in July there's 31 days, so we would take 7.44, divide it by 31, and we come up with 0.24. So the daily PET is 0.24 for CIMIS Zone 8. Now we're going to talk about water behavior in soil. So here, this is a chart that is from the Rainbird textbook, and it's an example of a column of soil and how water is going to behave in that soil. So first we have hygroscopic water, which is basically water that's being held too tightly within the soil, and plants are unable to draw that out. Then you have capillary water, which is in the available water column. That's moisture that's being held in the pore spaces of the soil, and it is available for roots to draw from. Then you have gravitational water, which is basically water being applied. And so plants can't drink it as fast as it's being applied. So as it's being applied, it isn't until it's being held in this available water column that it becomes readily available for plants to use. Down here we have the permanent wilting point, which is in between available water and your too tightly held hygroscopic water. And if you let your water level get down to that point, it might be to the point of no return. And permanent wilting point, or PWP, plants are no longer able to spring back from that. You may have had plants that look like they're not quite going to make it, and they're very droopy and flaccid, and then you apply some water and they bounce back up. That means they just hadn't quite made it to their permanent wilting point yet. Okay, so field capacity. Field capacity represents the boundary between gravitational water and capillary water. So here we have, it's the upper limits up here for soil moisture that's usable by plants. So here's the maximum useful level of water in your soil. So if you apply any more than this, then you've applied too much and it's not useful. So available water is the amount of water that's readily available for plants to use. So this chart from page 20 in the Rainbird textbook, figure 11, are the characteristics of various different types of soil and how it applies for irrigation and water retention. So here in this example, we have sandy soil for a soil type. Its texture is coarse. Its soil components, depending on its makeup. So a sandy soil component has a very high intake rate, as you can imagine. Imagine pouring water into a sandbox. It's not going to hang on to it very long. It's going to drain in very quickly. Its water retention, how long is it going to hang on to that water? In a sandbox, it would be very low. Okay, so then also, so if there was a little bit of loam in that sand, its intake rate would still be high, it just wouldn't be very high, and its water retention would be low instead of very low, and that's because some loam was actually present in the sand. So then if you have loamy soil, depending on its soil texture, ranges from moderately coarse to moderately fine. Its intake rate ranges from moderately high to moderately low, depending on its soil texture and components of the soil. And then clay soil has the very lowest intake rate and the very highest water retention. So why this is important in irrigation design and irrigation application is keeping in mind that once you know what your soil type is, that will also help you decide how to behave and how to design your system. If you have sandy soil, you don't want to apply your water very slowly, say in a drip system with individual emitters very far apart from each other, because water is not going to have a lot of lateral movement. The intake rate is really high. The water wants to go straight down. So the opposite happens here with clay soil. If you apply water too quickly, then that water is eventually going to end up running off because its intake rate is too low. It can't drink it very fast. But its water retention is pretty high. So what that means is in scheduling for very sandy soil is that you need to irrigate it more frequently because the soil isn't able to hang on to much of that water. Whereas clay soil, you wouldn't want to water it too frequently because field capacity will already be filled up. There's no more room for more water. So you might as well irrigate less frequently because your soil is able to hang on to that water for a longer period of time. Okay, in this figure 13 from the Rainbird textbook, it shows the wetted pattern for various types of soil. So for coarse soil or sandy loam, the wetting pattern is that it tends to go down more than it goes out. And in this example, they're showing the maximum wetted diameter is 1 to 3 feet. And the available water for coarse sandy loam soil is 1.4 inches per foot. And so what does that mean? What that means is imagine a column of soil that's 12 inches deep. In that 12 inches of soil, there's 1.4 inches of water that's available for plants to use that isn't being too tightly held and is available for the plant to use. Okay, so then as we go down through medium loam soil, you'll see that it doesn't tend to go straight down. It does have a little bit of lateral movement. Its wetted diameter is from 2 to 4 feet, and its available water is 2 inches of water per foot of soil versus 1.4 for coarse soil. Then when you get to fine or clay loam soil, you'll see that there's not a whole lot of infiltration going on very quickly. It's mostly lateral. So you'll get a larger diameter of wetted area because the water tends to hit the soil and move laterally instead of down. The other thing you'll notice is that the available water in this clay soil is 2.5 inches of water is being held as available to irrigate or to feed plants, versus 1.4 inches in the coarse soil. So again, what that means is, frequency of irrigation. You can go a longer time without irrigating again if you have clay soil than you can if you have coarse soil. So over here, figure 14, determining the soil type. We will do some more soil determination exercises later on in the chapter when we get to the Quell curriculum. But here's just some basic characteristics of soil to keep in mind. So coarse soil, soil particles are loose, squeezed in the hand. When dry, it falls apart when pressure is released. Squeezed when moist, it will form a cast but will crumble easily when touched. So you can almost envision that if you took some sand in your hand that was moist, what that would look like if you squeezed it and then you let go, that if you kind of jiggled it a little bit, it would start to kind of fall apart pretty easily. Medium soil has a moderate amount of fine grains of sand and very little clay. When it's dry, it can be readily broken, and squeezed when wet, it will form a cast that can easily be handled. So you're able to kind of perhaps manipulate the soil in your hands a little bit, whereas coarse soil kind of fell apart when you open your hands back up. Okay, so fine or clay soils, when dry, may form hard lumps or clods. When wet, the soil is quite plastic and flexible. When squeezed between the thumb and the forefinger, the soil will form a ribbon that will not crack. So kind of like a growing piece of soil as you have moist fingers with the fine clay soil in your hand. Okay, so here we have a few charts that I'm going to show you that you'll see throughout the semester that upon first glance might seem a little bit intimidating. First of all, remember that anytime in the Rainbird textbook, when you see green text, that is metric. Also, if you see it in parentheses, that also probably means it's metric, and just ignore it. So if you can, when you see green, just don't look at it. We're not going to be using metric calculations because why? So pay attention to just the black text, not the green. So what this figure 15 is about is what is the maximum precipitation rate of water that can be applied on various degrees of slope. Okay, so when we talk about maximum precipitation rate, We haven't got into talking about precipitation rates quite yet, so let me just give you a quick analysis on what that is. So basically, your precipitation rate is at what rate water is being applied to a surface, and it's rated in inches per hour. Okay? So, in this particular case, the maximum precipitation rate in inches per hour changes depending on the soil structure that you have, and it also depends on the slope that you have. So the steeper the slope and the heavier or finer the soil is, the slower intake rate that soil will have. So one way to envision it is if you were on a sandy beach and you had these rolling hills and you were pouring water on them, it will probably be able to soak in that water as fast as you give it. So in this particular example, coarse sandy soils on a slope of 0 to 5%, if it was covered, say with mulch or plant material, it can handle up to 2 inches per hour of precipitation. It also says it's the same for bare soil. But as you start to have a slope, you'll see that that number will go down. So over here, this is a pretty dramatic slope of 12% or greater, but I need to show you that for sand to make a difference. So here, if it's covered, it can still drink up about 1 inch an hour, and bare 1/2 inch an hour. But let's take a look at this contrast between coarse sandy soil and heavy clay or clay loam. So here, covered 0 to 5% slope, heavy clay can only absorb 0.2 of an inch an hour of water, where sand was 2 inches. So 1/10 of the amount of water can be drank up by heavy clay soil than it can for coarse sandy soil. Now take a look at what happens when you have a slope. So if you have a slope, it's very difficult to apply water at any rate and have it not start running down the hill. So instead of thinking of a sandy beach and pouring water on it, think of a concrete sidewalk, because that's basically what we're looking at, and how fast you can apply water and have it actually soak in. So then everything else falls in between. You'll see that 0.20 is the lowest number here, and 2 inches being the highest. The people's soil is going to fall somewhere in between those two numbers. Now imagine for a minute, we're talking about precipitation rates. Normally we're talking about sprinkler precipitation rates or drip irrigation systems, how much water is being applied to an area in inches per hour. But for a moment, think about the Weather Channel, and when you wake up in the morning and you listen and you hear that we got 1 inch of rain overnight, and that number is a big number. So if you think about it, we got 1 inch of rain overnight versus this chart is talking about 1 inch of water in an hour. So you can imagine that that's quite a bit of water that's being applied here. So how this works out in an irrigation system and why this is important is trying to match or get as close as you can to the infiltration rate of soil by what you're applying. So if you are going to be using a standard sprinkler nozzle, here is the application rate. So this is a basic pop-up spray head that has a radius of 15 feet, which means it's going to spray 15 feet in each direction at 30 pounds of pressure. It's going to have equivalent to 1.58 inches per hour of rainfall. Okay, so let's scooch on back up here to this chart for infiltration rates and look for something around 1.58. So that means anything finer than lightly sandy loams, that application rate is going to be too high. So what can you do about that? There are a few things you can do. One, you can choose a sprinkler head that is still efficient but has a lower precipitation rate. So it applies water slower but still gets you close to the same radius. So the numbers I picked here was to be consistent with 30 psi, 30 psi, and 30 psi. So here we had a radius of 15. Here we have a radius of 13. So it's a slightly smaller radius. But check out the precipitation rate number is lower. And that's because it's applying water at a slower rate. Now this number here, 0.64, if you look up here at this chart at the maximum precipitation rates, you'll see that there's a couple more different types of soil that would be more compatible with this precipitation rate application. So here, anything above silt loams would be okay for this. Okay, so now take a look over here. This one is also a reduced precipitation rate, multi-stream, multi-trajectory nozzle, and at 30 psi, it has a radius of 12 feet, so it's also a smaller radius. It has a precipitation rate of 0.45. Okay, so now that means that there's only one type of soil in this particular example that this would be applying too fast. Okay, so that's where another method comes in, and that's where I mentioned earlier about cycle and soak. So you can see it's very difficult to find any type of spray system that can be used with various types of soil and be able to keep up. So being that it's not really very realistic, what you can do is cycle and soak. And cycle and soak means basically you irrigate for a little bit, then you turn it back off, let it soak in, and then give it a little bit more. That way, let's just say that your water requirement meant 10 minutes a day, but you couldn't quite do 10 minutes. But let's say you could do 5 minutes. If you could do 5 minutes without anything running off, that means you could cycle and soak, have 2 different cycles. It would come on for 5 minutes, wait for however much time you needed it for, and then have it run for another 5 minutes. That way it still got its entire 10 minutes, but broken up into pieces. Okay, so in this example, what I'm showing you here is still the soil texture maximum precipitation rate, but with an example of drip irrigation. And again, these charts can be a little intimidating, but all you got to do is zone in on what you're looking for, and then you follow the charts. So let's just say that we have loam soil. And so we would find our soil right here, loam soil. We would travel down, and then it tells you what emitter flow rate you would use. And this is inline emitter tubing made by Netafim USA. And here it's 0.4 gallons per hour, whereas the flow rates on the previous chart were all for gallons per minute. And here we have an emitter spacing of 12 inches. And then the lateral row spacing, it means how far apart are your rows of drip tubing. 12 inches, 14 inches, and 18 inches are what they recommend. Okay, so let's just pick one so we can take a look. So 0.4 gallons per hour, 12-inch spacing, and let's pick 12-inch lateral spacing, gives us a precipitation rate right here of 0.64. Okay, so if you look up here at this chart, that fits right about in here. So that application rate would work for all of these types of soils, only it would be a little slow for this upper portion here. And again, you still might need cycle and soak even with a drip system. It might still apply it too fast. If you wanted to slow it down just a little bit, you could space your lateral rows out a couple more inches, pick 14 inches, and that would drop your precipitation rate down to 0.55. If this all seems like too much right now, just hang tight, because in the next couple of chapters, we will start getting into calculating precipitation rates and understanding how the flow rate and these numbers come together. Okay, so that is it for Rainbird Chapter 2 and 3 and the CIMIS references.